Well, ho, Aion Mellon. My name's Joe. People call me Mr. Mellon. Welcome to the final expansion video for explaining the Holy Grail of physics. Thank you for tuning in. This has been an incredible journey from the start all the way until now. So, happy 420 for those of you out there. I'll tell you what, I wouldn't have ever been able to focus and kind of chill if it hadn't been for me having my medical card. It was a lifesaver. So you say what you want about it. I don't really give it two thoughts anymore. You probably shouldn't either. Move on. That being said, we're going to go ahead and surmise the last two papers all in this video, and then we're going to break down a list of supporting experiments that we already have at our disposal to kind of show what we're talking about here and why it's right. So that being said, all right, let's get to it. The macroscopic flow and the origin of time. To follow along with the mathematical proofs and derivations connecting the physical flow of space to the generation of time, you can refer to the following sections in the 108-page QSM Treatise. So that's where you can go. We're going to start off on page 78. All right. Section 40.1, equation 220. The vacuum is not empty. It's a non-Newtonian fluid. The effective viscosity of space scales with the interaction frequency, the shear rate of the matter moving through the lattice grains. That equation there, it kind of breaks it down. So as things are moving through space, it's displacing space. We can now calculate that. And we actually see those effects as well. Next up, we're going to go on to page 80. It's 2 pages down, equation 222. All right, now I touched on this before, but this equation, it's the macroscopic quantum wake scales to the macroscopic galactic halo. It uses a vacuum Reynolds number, which defines this transition. So we use that to figure out the overall size of the galactic halo. It's in a fluid. It's displacing that fluid, and it's moving in accordance with that flow rate against, relative to the grain of space itself. So that's kind of important for being able to calculate certain things, to know what's flowing, how fast, etc. So, and if you're looking at page 220 or equation 222 on page 80, 41.2, it goes through and explains how that galactic viscosity constant that you can calculate for each galaxy actually fits and works with the database. They use the SPARC database, Spark database, for that, and that was then it shows the math for it. So that's public information. They release their studies. Next up, we're going to go down to page 82 to 83. So section 42, 4.1, equations 229 and 230. What this says is a photon has zero rest mass because it has a net displacement integral over a full cycle that is zero. So it's a purely reactive wave of the Higgs field transporting energy without displacing the medium. So it's using the lattice itself to flow. And that equation there, those two equations they show you that. It really is. It makes sense when you realize that they've been talking about the sea of space for the longest time, and it's technically right. They just didn't know what the sea was made of. All right, next up, we're going to go to number 4, which is the galactic dynamics and the dark matter illusion. It's on page 87, section 45.2. All right, so look at equation 239. What the concept here is we got flat rotation curves that do not require invisible dark matter particles. The velocity simplifies to a constant determined by the ratio of shear velocity to the vacuum density. And then it shows the equation there. What that means is because that dark matter halo is actually bigger than we give it credit for, that's why they hold together the way they do and rotate the way that we see them to rotate. It's pretty straightforward when you realize it's spinning in a fluid that has properties, but is at the same time superfluidic. It's not, there's no resistance to it. It's just simply the interactions of the particles moving that grain of space. Next up, we're going to go down to page 96, section 52.1. All right, so equation 265. Here's the concept. Inertia arises from topological friction, but it's a hydrodynamic resistance of the vacuum that is dimensionally equivalent to the thermodynamic cost of processing information. So as it's displacing this moment-by-moment grid to move through space, it's interchanging. That takes a so-called balancing of it. It's a thermodynamic cost of processing it. It takes whatever momentum it already had, and it uses that to move what's in front of it, while the lattice itself closes behind it, just naturally. So it does leave a wake. We see that wake. They don't realize that yet, but they will. They'll get to figuring that out. Now, how fast these bubbles of matter move through space dictates the cost of time. How fast does it travel from one spatial unit to the next, Depending on how big those base units are, will depend on the speed at which we see it moving through that space. So on page 96, like I said, equation 265 kind of gives you that equation and shows you, hey, this is how to calculate that difference. Next up is on the very next page, page 97 and then 98, equation 272. So time is not a coordinate, it's a process. The physical time derivative is identified with the decay rate of the Higgs amplitude mode. The universe evolves because the vacuum substrate is thermodynamically relaxing. And also bear in mind, if that substrate cannot move, time stops. There can be no moment to moment if it's completely full in this particular location or another. So time ceases to be, and you just have an object. It will clearly decay in accordance with what we see. Ultimately, the Higgs does have a part in that. but not for a very long time. Little grains of space, ultimately, just pure space. So, all right, next up, we're going to go ahead and just go through a quick rundown of verified experiments that support this work. I'm just going to list them off. You can find them in the paper as well for each relative section. First up, we've got the giant noise shot in superconductor / ferromagnet junctions. All right, this experiment, it's a measurement of current across vanadium junctions revealed in an anomalous excess noise. A Fano factor of approximately 100, representing a 2 order of magnitude discrepancy from standard quantum transport theory predictions. QSM mathematically identifies this as the acoustic signature of the vacuum geometric displacement. The energy cost required for a single electron to displace the vacuum lattice perfectly matches the macroscopic Josephson coupling energy of the junction array, proving inertia acts as a topological friction. They've seen this. They just don't have. They call it an anomaly. I don't know why. If they finish the math, it won't be an anomaly. Next up, Semi-Dirac Fermions. In 2024, they had a magneto-optical spectroscopy experiment on the topological nodal line semi-metal zirconium silicon sulfide. It confirmed the existence of quasi-particles that behave as massless Dirac fermions in one direction and massive Schrodinger fermions in the perpendicular direction. It's an analog for how space itself works. So they've seen this in materials. Space works the same way, just in a different way. But this solid-state discovery is an exact physical realization of the angle of attack mass generation mechanism. It proves that the mass is a function of geometric alignment. Moving with the grain yields linear dispersion, while moving against it yields quadratic dispersion. So we have a flow to us, and we have mass because we're going in this direction. So that's how that works. Number 3, the Magnon-Cherenkov Effect. In internal wakes, the picosecond strain pulse experiments moving through a magnetic lattice were observed emitting a Cherenkov cone of magnetons only when exceeding a specific velocity threshold. QSM validation of this, it provides a laboratory proof of inertial thresholds and that the geometric wake exists. It physically confirms that the mass is the energy lost to the medium when an objective geometry moves faster than the lattice's relaxation time. That little light that they see from bubbles in water that they couldn't explain, there you go. Number 4, Einstein-de Haas Effect in dipolar BECs. So in 2026, an experiment observed the Einstein-de Haas effect in an Europlum Bose-Einstein condensate. When the internal spins of the atoms relaxed, the fluid spontaneously generated macroscopic vorticity without external stirring. This validates the hydrodynamic coupling of time and space within QSM. It physically proves that the amplitude mode, spin and time, can be mathematically converted into the phase mode, vorticity and space, confirming that they are exchangeable forms of hydrodynamic energy within a viscous fluid. We just haven't realized how much that is relative yet. Number 5, speaking of relativistic plasma stability, the fireballs they seen at CERN. So the experiment, the anomalous stability of high-energy relativistic plasmas, such as the fireballs observed at CERN, which persist far longer than predicted by standard hydrodynamics. Standard theory predicts that which persists far longer than predicted by standard models. Standard theory predicts that the rapid turbulent explosion should dissipate the fireball rapidly, fast. They shouldn't see it last that long. But because they do, it's technically interacting with the fluid they don't see. That's what's giving it that extra life. So they've seen that at CERN. Number 6, phase transitions in 2D perovskites. I don't know how to say this word. I'm sorry, I'm not going to even lie. But they did laboratory scale phase transitions in 2D materials, demonstrated that optically exciting the Higgs amplitude model or mode drives the material from a low symmetry phase to a metastable tetragonal phase. This serves as a condensed matter analog for metric saturation, proving that the Higgs-driven energy density threshold, the vacuum yield point, can physically restructure a lattice. So they have done experiments with 2D materials. They have seen analogs for this stuff. Number 7, the PRad experiment, the proton radius puzzle. They utilized a windowless gas target and an ultra low, measurement or way to measure the proton radius. An ultra low is probably cold. I don't know what the equation is here. I just have notes in front of me. So, but the way that they did the experiment, it led them down to a measurement of 0.831 femtometers. Converged with the muon experiment, which was 0.841, deviating from other experiments where they found 0.875. So the variable probe hypothesis, if they mess with the board, they're going to mess with the reading for the proton. And so it has a geometric depth dependent on the probe's angle of attack. The constrained conditions force the electron probe into a transverse mode, penetrating the vacuum grain and measuring the bulk radius rather than the surface radius. So there's a difference there. The way that they did their experiment changed the result that they got, and they didn't understand why. But QSM explains that the board is something. They have to take that into account. Number 8, the muon G2 anomaly. So they have at Fermilab a muon G2 experiment that confirmed a discrepancy from the standard model predictions. It suggests the hadronic vacuum polarization explains the anomaly. But the QSM analytically derives the HVP term as hydrodynamic viscous torque. Because the muon spin vector is oblique, it experiences a conservative geometric potential difference across its topology, providing a dimensionally accurate physical origin for the extra polarization. So wrap your head around that. Galaxies Without Dark Matter. This is one of my favorites. I know this one. So the galaxies without dark matter, they coalesced in a bit of a different way, and their angle of attack relative to the grain is different. So they have a narrower cross section. They don't have a need. They don't leave a big enough wake based on the matter and how it coalesced in the first place. So the ultra diffuse galaxy of NGC 1052 DF2 exhibits velocity dispersions consistent with purely stellar mass, revealing a lack of dark matter. And so again, the halos only form when the vacuum turbulence breaches a critical Reynolds transition number, placing it squarely in the laminar. And when that Reynolds number is too low, it places it within the laminar flow for the overall mass of everything, and it has stellar mass without generating a viscous wake. It's as simple as that. And last up, I know this has been a long video, but last up we're going to do the S8 cosmological tension. A statistical discrepancy between clustering of matter predicted by the early universe, the Planck CMB, things like that, and observations of the late universe, the weak lensing surveys, etc. QSM adds a viscous dampening term to the Jeans equation representing the vacuum bulk viscosity acting on structure growth. Applying to the calculated vacuum drag over the age of the universe yields a theoretical approximation of 0.762, which directly matches observational data. So the reason why galaxies are moving apart at different rates and we see dark energy acting at different rates is because we didn't finish the math. QSM takes that into account. It turns into a dynamic system, and bada bing, we're done. Well, now we can see why things move at different rates, why the universe moved differently earlier on as it does now, why there's a curve to it. So, but that is the end of my final recap for the paper. We're going to move on to other topics for future videos, but I do appreciate you guys watching through all this. I hope it's been informative. I hope it answers some questions for you. And again, thanks again. Ho Aion Mellon, and may peace be with you. Stay blessed, everyone, and take care.